Welcome to this new video. In this video, we are going to finish section 2.2. So last time, we proved the following important theorem, one of the main theorems of this course, which says that a holomorphic function on an open set is analytic on the open set, on the same open set. And we proved the following, actually, that for any point z0 in omega, and if we take r to be the distance between z0 and the complement, this is just omega c, or the boundary of omega, there's an error here. Okay, so this is, so bz0r is the biggest disk contained in omega. And if we take a circle in this disk, then actually we can write f of z as a power series about z0. The radius of conversion is exactly this distance. And there was a formula for the coefficients. The formula is given, so the nth coefficient is 1 over 2 pi I times the integral over the circle of f of u over u minus z0 to the power n plus 1. And actually, so gamma actually can be taken any disk inside, actually, of the same center. So we have a choice in R0. So this works for any R0 here. Okay, and we shall see later, actually, that it's true if gamma is a closed loop, is a loop different, not necessarily a circle, actually. Okay, so one corollary of this is that if f is holomorphic, then actually f has derivatives of all orders, and there's a formula for the nth derivative at z0, which, and z0 is arbitrary actually here. Why? Because we know from chapter 1 that there is a relation between the coefficients and the nth derivative. So an is actually what? Is the nth derivative divided by n factorial. Okay? This is the first corollary. Now we are going to draw some other corollaries, actually, that follow from this big theorem. Okay, next result. The derivative of a holomorphic function is itself a holomorphic, and this was not clear from the definition. But now we know why this is true. Let us prove this. So in particular, if a function has an antiderivative, then it's necessarily holomorphic. So actually, at the beginning of this chapter, we raised the question or the problem of existence of antiderivatives, and we saw that not all functions possess an antiderivative. And I told you that we need two conditions, one on the function and one on the domain of the function. Okay, so holomorphy is actually a necessary condition for possessing an antiderivative, because the derivative of a holomorphic function is holomorphic. Okay. So for example, yeah, this is z bar here. So the function z bar has no antiderivative. Why? Because it's not holomorphic. It's nowhere holomorphic. And the function modulus of z squared also has no antiderivative because it's holomorphic only at z0. So if a function possesses an antiderivative, then it's on an open set, actually, it should be holomorphic on that open set. Okay? So this is the questions that we always ask, actually. Second, the consequence of the analycity of holomorphic function is known as Morera's theorem. It's the converse of Cauchy. Remember that Cauchy theorem states what? That if f is holomorphic, then the integral over the boundary of any triangular region in omega is 0. Morera states the converse. If the function is continuous and the integral over any triangular region in omega is 0, then f is holomorphic. Now this is an easy consequence of our theorem. Why? How do I prove that f is holomorphic on omega? We have to prove that it's holomorphic at every point of omega. So pick a point z and take a disk, a neighborhood about z, okay, contained in omega. This disk is of course convex. So by theorem 2.2, remember, f has an antiderivative, right? We already observed that because this condition actually, since by convexity, this condition is equivalent to saying that the integral over any triangular loop in omega is of f is 0. So condition 4 actually states that f has an antiderivative, right? Now, so an antiderivative is necessarily holomorphic, so f is holomorphic, okay? And it's holomorphic on the disk, and in particular at z. Since z was arbitrary, we are done. So we proved that f is holomorphic on omega at every point of omega. So it's an easy consequence of this remark, actually. Next result, remember that when we proved the second version of Cauchy, what is the difference between version 1 and version 2 of Cauchy? Cauchy assumes that f is holomorphic on omega, the version 1. Version 2 assumes that f is continuous on omega and holomorphic on omega without a point. And I told you that actually if this is true, then f is holomorphic on the whole of omega. So version 2 is not something new actually, but you didn't know that. We needed version 2 actually to prove Cauchy's integral formula, which allowed us to prove the analycity of holomorphic functions. Okay, but now we know that version 2 and version 1 are just equivalent. Okay, so version 2 is nothing new. So why this is true? Because by version 2, the integral over the boundary of any triangular loop in omega is 0, right? Now, by Morera's theorem, f is holomorphic, and that's it. Very simple. So version 2 and version 1 are equivalent. Okay, but we didn't know that when we proved them. Okay. Next result, next consequence of the analycity of holomorphic function is Cauchy's inequality. So consider a holomorphic function on a disk. So we know that we can expand f in a power series about z0, right? If we take a circle of center z0 and radius r, so a circle inside the disk actually, as we did in Cauchy's integral formula, okay? And if m of r is the maximum of the modulus of f on this circle, which is compact actually, so modulus of f is continuous and the circle is compact, so there is a maximum value that depends usually on the circle, okay, which has radius r. So I call it m of r. When r varies, the circle varies, and so the maximum varies. Then there is a very simple inequality relating the modulus of the coefficients and m of r. So this is the inequality. The modulus of the nth coefficient of this series is bounded from above by the maximum of modulus of f on the circle divided by r to the n. And this is true for all n. Why this is true? Because if we go back to the proof of theorem 2.6, we had the formula for the coefficients. Okay? And this is the formula. So now, if you take the modulus, then this becomes 1 over 2 pi. And the modulus of the integral is less than the length of the integral times the maximum of the modulus of the function inside. This is the fundamental estimate. Okay, so this is the length of omega, which is just 2 pi r. Now, if you look at the modulus, so the modulus of the numerator is modulus of f of u, and the modulus of the denominator is u minus z0. If u varies in gamma, which is the circle of center z0, then this is just the radius of the circle. So the modulus of the function inside an absolute value is less than, to m of r over r to the n plus 1. Right? When I simplify by 2 pi and by r, I get just m of r divided by r to the n. Very simple formula. Corollary of this is Liouville's theorem. Okay, but first the definition. What is an entire function? An entire function is just a holomorphic function on C, on the whole complex plane. So we know actually from the proof of theorem 2.6 that we can expand f about any point in a power series, and the radius is infinity because there's no singular points on C. Okay? So in particular, if you expand about 0, then we can write f of z as sigma of a n z n with an infinite radius of convergence. This was the remark following theorem 2.6. Okay, so we have a simple formula for the radius of convergence without even computing the coefficients. So Liouville's theorem states what? It states that if an entire function is bounded, then it's necessarily constant. Okay? Why this is true? This is a consequence of Cauchy's inequality. So first write f, expand f in a power series about 0. And take any positive number r, arbitrary. And since f is by assumption bounded, let a be a bound of the modulus of f. Okay? So when I say f is bounded, it means the modulus is bounded. By Cauchy's inequality, the modulus of the nth coefficient is less than m of r over rn when m is the supremum over the circle, but the supremum of the circle is less than a because it's an upper bound of, okay? So we get modulus of an is less than a constant, which does not depend on n and neither on r, it's a constant. Okay, it doesn't depend on r, over rn. But r was arbitrary, okay? Because the radius is infinity. The radius of convergence is infinity, so I can take any positive number. So if we let r tend to infinity, we have two cases here. If n is 0, this just r to the 0 is 1, so this doesn't tend to 0, just a constant. However, if n is at least 1, then r to the n tends to infinity, so a over rn tends to 0. Okay? And this is true for every n bigger or equal than 1. So we get that the coefficients are 0 actually for all n starting from 1. And therefore, we cannot say anything about a 0 actually. So actually, all the terms, all the coefficients of this series vanish except the first one. So f of z equal a0. Okay, so a bounded entire function is constant. Now, a very interesting consequence of this theorem is the fundamental theorem of algebra, or the Lambert theorem. It states that every non-constant polynomial with complex coefficients has a root, has a complex root, not necessarily real. And you know actually this from high school, but I think you never proved it because all proofs are actually difficult. And most of the proofs, there are so many proofs actually of this theorem, most of them use topological ideas. And I was told that there is one that uses only algebraic tools. I don't know about it. But the proofs that I know use algebraic ideas, topological ideas. Okay? In this course, actually, this is a direct consequence of Liouville's theorem. But actually, look at what we did to prove Liouville's theorem. We had to develop a big machinery, to develop a theory, actually, in order to prove Liouville's theorem. Once we have Liouville's theorem, now this becomes an easy consequence. And by the way, you may restate this theorem as by saying that C is algebraically closed. Okay, the field of complex numbers is algebraically closed. So this is just a rephrasing of the theorem. So consider a polynomial which is not constant, and let n be the degree of the polynomial. So the leading coefficient is not 0, because otherwise it will have a lower degree. Okay, now the remaining coefficients could be 0, doesn't matter, but the leading coefficient is not 0, and n is at least 1 here. Okay, because it's non-constant. So I will reason by contradiction. I will assume that P does not vanish. Okay, so I will consider 1 over P. But before that, if I factor by z to the n, and then takes the modulus, all these terms here in modulus tend to 0 as modulus of z tend to infinity. Okay, so we are just left with the modulus of an times modulus of zn, and this quantity actually tends to infinity. So this is a remarkable property that the modulus of a polynomial, a non-constant polynomial actually, tends to infinity as the modulus of the argument tends to infinity. Okay. Now, suppose that P has no roots in C, so it never vanishes. So I can consider 1 over P. And 1 over P is not necessarily a polynomial, but it is a holomorphic function. Okay, because the inverse of a holomorphic function is holomorphic. We didn't prove that, but in principle, you proved it in the first course on complex variables last year. And this proof is similar to the proof that the inverse of any differentiable function of a real variable is also differentiable, provided it does not vanish. So I have a holomorphic function here. And what do we have here? At infinity, the modulus of this function tends to 0. So this function tends to 0 at infinity. Okay? So what does this mean? It means in particular that I can make this quantity less than any number I like if modulus of z is large enough. So this can be made less than epsilon for r large enough. So in particular, I take epsilon equal 1 in the definition of limit. So in particular, I can make 1 over p in modulus less than 1 outside a disk. So if the modulus is large enough, this quantity, since it tends to 0, it's less than 1. Okay. So now we divide the plane into two regions. The disk of center 0 and radius r, the closed disk, and the outside of the disk. So on the outside of the disk, 1 over p is bounded by 1. And on the disk, which is compact, this function is continuous, so it's bounded. So 1 over p in modulus is bounded on the disk because the disk is compact, and it's bounded outside the disk. So this is actually this is a topological idea actually. So boundedness of a continuous functional compact set is a topological idea actually. So actually 1 over p is bounded on C. So that's it. We have an entire function, because it's holomorphic on C, which is bounded. By Liouville's theorem, it's constant. So 1 over p is constant, so p is constant. But we assume that p is not constant. And that's it. This proves the fundamental theorem of algebra, or D'Alembert's theorem. Okay, now the last two results deal with the maximum principles. So there are two maximum principles. So recall the following definition. Consider a function g defined on an arbitrary topological space, or because we need the notion of neighbor. So I will take x equals c here, but the definition is very general. So consider a function defined on a topological space that takes values in R, and consider a point in that topological space. we say that G has a local maximum at the point A if in a neighborhood of A, in some neighborhood of A, G of A is the biggest value of G. Now this is locally because it holds in some neighborhood. If this inequality holds for every x in capital X, then we have a global maximum. So we have to distinguish between local maximum and the global maximum. A global maximum is indeed a local one, but the converse is not true, as you may check. Now, sometimes we say relative maximum, okay? And we have a completely similar definition for local and global minima. Okay, now the strong maximum principle. So consider a holomorphic function on an open and connected subset of C. If the modulus of f, so it's important to talk about the modulus of f because f takes values in C, so I cannot, there's no order relation on C. So if the modulus of f is actually a function from C to R, or from omega to R. So if the modulus of f has a local maximum at a point in omega, then f is necessarily constant. Okay, and this is one of the main differences between real valued functions and complex holomorphic functions. Why this is true? Because by assumption, there is a neighborhood of A. So in particular, there is this neighborhood contains a disk of center A and radius rho, such that f of z in modulus is less or equal than f of A in modulus for all z in that neighborhood. Now, take a circle inside this disk of the same center, as usually we did so many times, and apply Cauchy's integral formula. So at the point A, so I can write f of A as the integral of 1 over 2 pi I times over gamma of the circle, positively oriented, of f of u over u minus A. And apply the definition of a line integral. So because you have a parameterization here, so it's the integral from 0 to 2 pi of f of gamma of t times gamma prime. And u minus A actually is just gamma of t minus A, which is REIT. So we did such computations. So now simplify by R and I and EIT, and we get 1 over, so f of A can be represented as an integral of, so 1 over 2 pi times the integral from 0 to 2 pi of f of A plus REIT. This is something very specific to holomorphic functions. It's not true for any function, actually. And now take the modulus. The modulus of the integral is less than the integral of the modulus, as you know. And now, because f of A in modulus is a local maximum, so in particular, of course, on the disk, and this is, so gamma is inside the disk. So in particular, the modulus of f of gamma t is less than the modulus of f of A, because this is a local maximum. Okay, and now we get what actually? This is just modulus of f of A because it's a constant, it doesn't depend on t. So what do we have? F of modulus of f of A is less than this guy and less than itself. So we have equality, right? So because this is a number between modulus of f A and itself. So all of these terms are equal to themselves. Therefore, if I rewrite them under the same integral, so we can write that the modulus, the integral from 0 to 2 pi of the modulus of f of A minus the modulus of f of gamma of t is 0, right? So just write this as, or if you like, multiply by 2 pi and write this as an integral. Or okay, or just consider these two. These two are equal, right? So just make the difference. If you do the difference and simplify it by 2 pi, you get this. Now, the function inside, as we observed, is non-negative because because modulus of f has a local maximum at a. So this is non-negative. And it's 0. And it's continuous, of course, as a function of t, because f is continuous. So we have the integral of a non-negative continuous function is 0. Then necessarily what is inside is 0, right? By continuity. So we have that f of gamma of t in modulus is equal to f of a in modulus. But r was arbitrary. So actually, any number z inside the disk can be written as gamma of t for some r, right? So actually, what we have is that the modulus of f of z is equal to the modulus of a for every z inside the disk, because every point inside the disk is the image can be written as gamma of t, can be written in this way, right? Because every z in BR is on some circle inside the disk, right? So here r is the modulus of z actually, and t is the argument of z minus a, if you like. So the modulus of f is constant on the disk of center A and radius rho. Now, I hope that in the first course on complex variables, you proved that if the modulus of f is constant on a connected set, then f is constant. Okay, this is an easy exercise actually that follows from the definition. If the modulus of a holomorphic function is constant and the domain is connected and of course open, then f is itself constant. Okay, in principle you did that as an exercise. If you didn't encounter this, it's proved in the lecture notes of Math 307. Okay, the course that we used to give, and we had much more time actually, so we used to teach more. So that's it. So f is constant on BA rho. Okay, now the principle of analytic continuation implies that f is constant on omega, because omega is connected. Okay, because we have f constant on an open subset of omega, and omega is connected, then f is constant on the whole of omega. Now, if omega is not connected, we cannot conclude that f is constant on omega, but just that f is constant on the connected component containing BA rho. So on other components, f could be arbitrary. Okay, and the last result is a corollary of this. So corollary 2.8, the weak maximum principle. So the result that I just proved is called the strong maximum principle. There is another form called the weak maximum principle. It states that if f is continuous, this is omega bar here actually, so there's an error. So f is continuous on the closure of an open set and holomorphic on the open set. Then the supremum of modulus of f on omega is the same as the supremum of modulus of f on omega bar, this is omega bar, and it's the same as the maximum. Actually, here omega is bounded, so this is compact and this is compact. This is omega bar here. Sorry for that. Right? So we have a double equality here. So otherwise stated, for a holomorphic function which is continuous on the closure of a bounded and connected set, actually necessarily achieves a maximum at the boundary. Necessarily. Now, it may achieve a maximum inside, but in this case, it's constant. Okay? So in general, the maximum is achieved at the boundary. Why this is true? So just have to prove two things. The first part of this inequality, the supremum over omega is the supremum over omega bar. So this is omega bar here. Now, since omega is less than is contained in omega bar, the supremum over omega is less or equal than the supremum over omega bar. So we have to prove the reverse. So I call small m the supremum on omega and capital M the supremum on omega bar. Please correct that. So capital M is the supremum over omega bar. So we indeed have small m is less or equal than capital M, because omega is contained in omega bar. Now, to prove the reverse inequality, consider the set of z in omega bar such that the modulus of f of z is less or equal than small m. Okay, now, since modulus of f is continuous, this is just the inverse image of the interval 0m closed under modulus of f. So A is closed, as you recall from the topology course, because it's defined in terms of large inequalities and involves continuous functions. So A is closed in omega bar, and therefore it's closed in C. So once again, this is omega bar. Please correct that. Now, since omega is contained, this is, yeah. Omega is contained in A. Why? Because M is the maximum over omega. So omega is contained in A, right? Since A is closed, we have omega bar is contained in A bar, which is A. So omega bar is contained in A, right? So actually A is equal to omega bar. So for every z in omega bar, modulus of f of z is less or equal than small m. So capital M is less than small m, right? So small m is equal to capital M. Please correct these inaccuracies in the writings. So, and actually here I didn't use the holomorphy of f, just the continuity. So this is true actually in every topological space. So the supremum of a continuous function on omega is the same as the supremum of the continuous function on the closure of that domain. Why? Because the closure of omega is so close to omega. It's actually really adherent to it. So cannot really separate omega from omega bar. So they are glued together, if you like. So omega bar is glued to omega. So continuity means that they have the same supremum. Now, the second part of the equality uses the holomorphy of f and the strong maximum principle. Okay, now we assume that omega is bounded. So omega bar is closed and bounded, so omega is compact. Omega bar is compact. So once again, please correct that. Therefore, the f in modulus achieves a maximum value at some point in omega bar, which is omega union. So this is omega bar again, which is omega union the boundary. Okay, this is something that we use so many times. So a continuous function achieves a maximum value on a compact set. Now we have two cases. Either A is an omega or A is at the boundary. If A is inside, this is true, this is just omega, then by the strong maximum principle, f is constant. And therefore everything is constant. F is constant on omega and therefore on omega bar. So this is just the same constant here. If A is at the boundary, then also we are done, because the supremum on the boundary, which is also a maximum, is less or equal than the supremum on omega bar, because omega bar, this is omega bar, because omega bar contains the boundary. And this is just equal to f of A because it's a maximum. Okay? But since A belongs to the boundary, it's less than the supremum. So all these quantities are equal. Right? And that's it. So this concludes section 2.2. And please, you can start doing the exercises. I will correct them next week. And I will post another video covering section 2.3 soon, okay? Because we don't have enough time. So you'll have to do some effort if you want to finish the program, okay? So thank you for your attention, and please excuse me for these inaccuracies. In the lecture notes, they are correct. So if you are a little bit lost, please read the proof in the lecture notes. Okay? Thank you for your attention.